This in the first part of this question to solve a log equation. And don't forget ln is actually the same as log to base e. So I'm just going to write a few logs down. Log to base 10 of 100 is equal to 2, because I'm saying, what do I raise 10 to the power of to get 2? It's a bit different from an exponentials where we're actually raising something to the power. In fact, it's the opposite. So have a little think. What's log to base 2 of 8? Well, this is saying, what do I raise 2 to the power of to get 8? And the answer is 3. I'm doing this non-calculator. Of course, in general, if you get log to base 2 of 7, you get a decimal. We tend to use our calculator for that, but I'm just trying to remind you of what they actually are because that will help us solve this equation. And then let me do another one. What about log to base 5 of a fifth? That's actually going to be minus 1 because 5 to the minus 1 is a fifth. So what we can do in this question is we have log to base e of 2x minus 3. That's saying, what do I raise e to the power of to get 2x minus 3? We actually know the answer is going to be 4. So we can undo the log. We can write down that 2x minus 3 must equal e to the 4. And that's our first step for solving this equation. The alternative way to think about it is that we could raise both sides to the power of e. Because e and ln are opposites or inverses, so they actually cancel out. And again, we're left with, well, the 2x minus 3 actually comes down, and we're left with 2x minus 3 is e to the 4. Okay, let's finish solving this. So we can add 3 to both sides. 2x is equal to e to the 4 plus 3, and therefore x is e to the 4 plus 3 over 2. And that is our exact solution. We don't want it as a decimal, we want it exact in terms of e. The second part of this question is unrelated. We've got a cubic polynomial dividing by x plus 2, and we're told the remainder is 2p minus 8. We're asked to find p. So for this, we need the remainder theorem. Basically, if we divide a polynomial by x minus a, then to get the remainder, we just put a into the original function. The reason being, just very briefly, is over here, if I have some sort of polynomial and I divide by x minus a, then I'm going to get some sort of polynomial out of it, and then I'm going to get a remainder, which let me call it r, which I still need to divide by x minus a. So if I multiply through by x minus a, I get f of x is this formula that's actually above, g of x, x minus a plus r. But we can see if I put a into the formula, then I'm going to get 0 for this term, and then the remainder. And that's a little proof, really, that the remainder is just f of a. Okay, I hope that made sense. Just a proof of the remainder theorem. But what we're being asked to do here then is, well, I'm going to call this f of x, the top cubic, and it's divided by x plus 2. The remainder theorem therefore says the remainder is going to be f of minus 2. That's the key thing. The factor theorem, by the way, is like a consequence of this. So if there's no remainder, then x plus 2 is a factor, and f of minus 2 would then be 0, because there's no remainder. So f of minus 2 will be, let's just sub in, minus 8 plus 4p. Use your calculator as you want here. Plus 4 plus 6. That is equal to 2p minus 8. So I've got 10 minus 8. I've got 2 plus 4p is equal to 2p minus 8. I can minus 2 from both sides, and minus 2p from both sides, but also minus 2 from both sides. 2p is going to be minus 10, which gives us our answer. P is minus 5.